Hello students, welcome back. We covered most of the standard materials from lesson 1B. Now we have some unusual topics left, and there may be some students who don't need it and want to skip. That's not going to kill you. We're going to talk about something advanced here. Now let's go back to the initial value problems here, and we talked about these examples. First example, rather standard. And here's the visualization. We have general solutions visualized in gray curves, those graphs. And then depending upon what initial condition we have, blue condition 0, 3, red condition 1, -2, they determine a specific graph. Those are solutions of the initial value problems. But this one was a little bit different because we had general solution with singularities. The denominator hits 0 at t is plus or minus square root of c, and in these particular cases, blue, red, and green, t squared minus 1, so plus or minus 1 at those points we had singularities. So we had different intervals of definitions, and consequently we have 3 separate solutions. Well, in terms of just algebraic function that we studied in college algebra level, 1 over t squared minus 1, that's just a rational function, just one function. However, in terms of solutions of differential equations, which come with intervals of definition, they are actually 3 separate solutions of 3 separate problems. We are going to go from there. Information flow. So we can consider solutions of initial value problem as an information flow that originates from the initial condition. So here's an example. Well, let's go back to the previous example as a matter of fact before going over to this. So okay, here's the initial condition, and the information flow as t gets larger and larger and larger goes up, up, up. And of course, if you go back in time, retrace where this information came from, you go back in time like this. And then y blow up to infinity, and when t is greater than 1, they're after the singularity, after the world ended, so nothing, universe ended at t equals to -1, so after that, no relation. As for this red solution, for example, here's the initial points, so you can consider it as information flow. Starting from here, information is flowing, t is getting larger and larger and larger, going down, down, down. And then if you go back in time, so present-day universe must have come from Big Bang, infinite energy coming down, 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 and about here, and then further, further, further. And then before the creation of universe, before t equals 1, we don't consider it. It's completely unrelated. And that's what blue, red, and green are all about. They're completely different problems. If you consider those in terms of information flow, things are a little bit more apparent. And then whenever you have a singularity that blocks the information flow, that's where interval of definition ends. After that, that's a completely separate problem. Let's go back to this again. I closed it prematurely, excuse me. If you just look at this rational function as a rational function as you have been doing in college algebra days, then it makes sense from negative infinity to positive infinity. That's the domain of this function, and at -1 and +1 we have vertical asymptote, and that's it. But we are not looking at functions here. We are looking at solutions of differential equations which come with open interval within which we have information flow, then we have actually 3 separate solutions regarding 3 separate problems. And here's another example. Depending upon C values, and depending upon x is less than 0 or greater than 0, we have a bunch of solution curves here. And how is information flow going over here? Something like this, or the other way around. Looks like purple do not go to brown. So do we have something like this? Well, that's something you can consider, but clever students must have thought of this already. If I take this parabolic path, wait a minute, from here I'm going back in time. Now I'm taking forward time. Going back in time, what does that mean? Already that's gonna ring a bell. If I'm around here at this point, and then going back in time will mean you're backtracing the history and then where everything came from, you see. But at the same time, we have here and then we have mirror image there. And how are they going to relate it? It's another headache. Does it really make sense in terms of information flow? Well, let's answer the question. In short, they're not related. Let's see. This is the implicit solution given. And finding out C value, that's not too bad. You should be able to do that. Plug in and then find out for C. And then we get the solution. Great. Getting solution is easy once you have the general solution. We got it. But finding out the interval of definition is entirely different matter. That's not going to be easy. So how do you do that? Let's try to find it algebraically only. And then let me show you the picture first. Picture later. Algebraic solution. Well, so for y, we have square root. Oh, whenever you have square root, you have to worry about plus or minus square root. And then inside has to be positive and things like that. So inside of the square root has to be non-negative. And as a matter of fact, I made a mistake here. It's great. Inside of the square root must be non-negative, but at the end point, you cannot consider derivative. And this is differential equation, so we have to have open interval. So the interval of definition must be on differentiation Therefore, I've tried it as an open interval. Okay, that is the interval of definition of this. You can find it using square root. It wasn't too bad. Or was it bad? So for y, and we have square root, inside of the square root has to be positive. Non-negative, yeah, but actually positive, that's what we need because we don't want the endpoints. We need open interval. Does it look good? Okay, let's go to the next example. How about this example? Finding solution, again, I can go quickly. I'll trust that everybody can do that. Here's a solution and plug in the value. X is 1 and y is 1/2, square root of 1/2, and then calculate C. That should not be too much of a problem. And we have it. All right? Now let's determine the interval of definition. So for y, and we're going to have plus minus square root, and let's see how that goes. So for y, plus or minus square root, and inside has to be positive. So we have negative infinity to 0 or that so which is it? Excuse me, I'm showing the answer here already. Pretend you don't see it. You have two intervals here, but only one of them is right interval. I should have hidden this. Pretend you didn't see it. Okay, you have two intervals here. Which is right? We have two separate open intervals, so they're unrelated. Only one of them is right. Where is this initial condition coming from? X is equal to 1 and y equals to square root of 1/2. So x has to be 1. X equals to 1 belongs to this one, not the other one. So first interval does not include the initial value, therefore second one. So this is the interval of definition. Let's go over here as well. Okay, that's not too bad. Okay, we have this, but this one is bogus, or this one, because of the initial condition. And let me show you the picture. So points here and there represent the initial conditions. At x equals to, let's see, 1 right here, y square root of 1/2. And then information flow is flowing this way as x increases. And then over here, information flow is moving in forward direction, x increases going up like this. Interval of definition, you can clearly see it from here to infinity. So it's, let's see, what is it? Is it 1 to infinity, or I forgot as a matter of fact. Was it? Oh, red one. 4/5 to infinity, so 4/5 to infinity. And this one is -4 to 0. -4 to 0. So you can see -4 here, -4 to 0. And then this one is a little bit hard to see, 4/5 to infinity. Now, how about these dotted part? Well, let's go back to this original differential equation and consider the special case when y is equal to 0. What happens when y is equal to 0? If I plug in y equal to 0, what happens? Something times 0 is equal to 1. I don't have anything there. So this x-axis over here, we have a singularity all along, do you see? So plug in y equal to 0 here, then left hand side is 0. 0 equal to 1, that doesn't make any sense. So this entire x-axis is singularity. So the top part and bottom parts are, as a matter of fact, not related. They look like they're connected. Look like they're connected like this, but that's just visual artifact. And that's why I separate this solid and dotted curves. If you look at in terms of information flow, you can see that the top and bottom are unrelated. Well, I'm getting really deep here, and I'm talking to rather self-selected students here. I already gave you fair warning before the beginning of this part. And if you don't really understand all these and then decide to skip, that's not going to kill you. In any case, the interpretation of initial value problems are related to information flow, and that's where the singularity concepts coming into play. And singularities have many aspects. It could be a single point where the denominator hits 0 or square root becomes negative and things like those. But as you saw in the last example with entire x-axis, singularity may be hidden. There are all kind of ramifications out there, case by case, and that's the difficulty behind differential equations, and also that makes this topic fascinating. Okay, do I have time to talk about something else? How about the fundamental theorem? I'll just mention it because our textbook author mentions it too, without proof, of course. Let psi be a double variable function of two variables, and it is continuous in a certain rectangle, T1 to T2 and A1 to B1. A1 to A2. Sorry about the typo. Okay. Then, initial value problem defined like this. The derivative is an expression of t and x, has a unique solution in an appropriate interval of definition if the partial derivative related to the second variable x exists and it is continuous. As a matter of fact, Lipschitzian condition is sufficient, but that's a little bit hard to check. So our textbook author decided to use this, what do you call the C1 condition, partial derivative exists and is continuous. We don't need all partial derivatives, sorry about that. That was for multivariable case. In that case, unique solution exists. We are not going to prove it. I have a proof in the appendix, but I don't know, I'll ever go back to that. This is a little bit more general situation. If you have system of differential equation, so we have many functions, x1, x2, x3, x4, and so on, many functions. All of them are single variable function, which has independent variable t, and then they're all intertwined. In that case, we need all partial derivative, because there are many, and all those exist and continuous in appropriate rectangle with respect to this variable over here. Then the initial value problem has a unique solution. So whatever you're doing is valid because of these fundamental theorems, as a matter of fact. Solution doesn't exist at all, then whatever analysis of solution we've talked about is completely meaningless. But it is meaningful because the fundamental theorem actually certified the solutions existed. Okay, that's about it. And we're going to come back and talk about direction field in the next video, and that one is going to be appropriate for everybody.